Okay, the recording has. We're still working on itself. Chat. Transcript of it started. So a couple of announcements first. So well done to everyone, or almost everyone, who has completed assignment 1. Yeah, we'll do the grading over the next roughly 3 weeks, and you should hear back after the break. It is not an easy assignment, so I trust people have tried your best, and the tutors have been supporting you. So don't, I guess, like get too nervous about how you do, because at the end, this class will sort of scale itself appropriately to somewhere. In some years, the assignment marks are uniformly very high. Then we had to set a very difficult exam. If your assignment scores are sort of spread out as a whole class, then we're not, like, as the instructor, I don't have to set a very hard final exam, which is easier for me to set. And I think the class, right? So basically, the top fraction of the class deserve to get an HT, and we will try and make that happen. And if not, there will always be moderation. So don't worry about. Hopefully, you're not worrying about your grades very much. There are some still questions coming in about grading and so on, and we'll gradually address that. So we should start today with 2 general announcements. First, I would like to ask if our 2 course representative volunteers, Taylor and Yuchen, whether they're here. And if you're here, please unmute yourself and say a few words about yourself. Maybe let the class see your face, and tell them about your mission and what you would like to hear from the class. I think I saw Taylor. Yes, Taylor is here.
I think Yuchen is not going to join us today. Hi everyone, my name is Taylor. I am an honors student at ANU. I'm studying advanced computing, and this is also my last semester at ANU, so I'm very glad to help here. So in this week, we will probably release a survey to collect some of your feedbacks regarding how are you feeling towards the first half of the course, towards the lectures, towards the labs, towards the assignments. So we are very happy to hear from you. And if you have any more specific feedback, you could also send me or Yuchen an email. And yeah, that's all. Thank you.
Thank you, Taylor. Yeah, if people have immediate questions, feel free to use the chat or unmute yourself and just ask. In general, I would say, as the fairly large lecture and tutor team, I'm here to help everyone learn. And hopefully, as a class of 300 students strong, we do that without too much suffering. So course reps are volunteers, and they have kindly devoted their energy and time to help everyone in this mission. So we're happy to hear from, like, basically everyone through course reps or directly. Since we've just like most of the class just submitted assignment 1, I saw this is also a good opportunity for people to reflect a little on your experience. I know this class has been, right, there are 2 known reputations. What shall I say? One is that it's very messy. The other one is very fast. So every year we try and do different things to help you guys. But right, so we wanted to hear from you about what seemed to have gone well, how have you learned, and what are the 1 or 2 things that we can tweak for this year's class and the next year's class. And as usual, like everyone, almost everyone here are experienced ANU students. Like the second half of the semester, the pace is going to pick up in terms of assessments. So we will be looking pretty closely and help people to navigate those. On a separate note, basically student services are running this particular session on navigating your degree. And they ask us, the course conveners, to pass this information on. I do know that especially for people who have a shorter degree, like a 2-year master's or even 1-year master's, yeah, choosing courses are pretty important, and there are changes in different course offerings and so on. So bring your question to that session, yeah, if you like. So since this is week 6, I'm just gonna say that week 7 and 8 we have both Mondays as holidays. If you have a tutorial on Monday, then feel free to join any other online tutorial the same week. I'll say this again on Wednesday in case people forget. But on the other hand, teaching break is coming, so I hope we all sort of take this opportunity to fix some breathing room and prepare for the second half of the semester. So this today we are going to spend the roughly hour and a half on kernels. Yeah, it's divided into 4 parts, roughly, with a brief recap and then 3 new parts, split between chapter 2 and 6. Right, and today's XKCD is essentially a pun on kernels. It's half of a pun, but this also says kernels itself is a loaded word. Last week, when we were talking about neural networks, I had this culture rant to you guys about there are many suitcase words in machine learning. And also there are overloaded terms in machine learning. So suitcase words have a general meaning, but you can sort of pack a number of different specific meanings to it. In terms of kernels, I feel this particular word as a technical term is not quite a suitcase. It's more like being overloaded again and again. For example, well, those of you CS students, you would know, oh, OS has a kernel, Linux have a kernel. That's different. And in this particular class, right, so if you go to the Wikipedia page, this was a snapshot last year. I don't know whether there are more being added this year. In terms of this class, we and this lecture and Wednesday's lecture were concerned with 2 particular meanings of kernels. One is called the kernel method for, let's say, classification and regression, as you will see. And then the second meaning, as we will get to first today, is called kernel density estimation. And the last, right, associated with that, we will be talking about kernel function or kernel matrices. There are positive semi-definite. These are tools for kernel methods. And reproducing kernels, kernel Hilbert space is also sort of in the general mix that we won't talk about it, but it's the formal theory behind like defining kernels. There's another important concept that I didn't highlight, so which is the kernel trick. It's called in statistics, but essentially in kernel machines, or this week we will be talking about representing a classifier as essentially the kernel function or inner product between your data point and other training points, and that is the essence of kernel machine, right? All right, so, and these concepts, they are related despite not being the same as, for example, kernels in image processing, well, which concerns convolution, which is related to KDE, but not quite. It doesn't do density estimation. Convolution kernel is the same as the convolution, right, basically, image processing kernel. Stochastic kernels are something different. That comes in, like, when we talk about different class of machine learning models, such as stochastic processes or things that me and my lab have worked on the past few years. Okay, yeah, anyway, so kernel is a very overloaded word. Just be careful when you see the word kernel, what you mean. we have seen this a few weeks ago, a few times. We have been talking about basis functions in linear models that helps classify points that are not linearly separable, right? So the general idea is if we can have an arbitrary number of powerful enough kernel functions, we should be able to separate any points that were separable in the original space, but in a nonlinear way. This, just to remind you, the so-called linear classifier is W transpose X plus bias term, and the kernelized version is W transpose phi, where phi is the kernel or feature vectors. So from the original input space, which is x1, x2, where we transform them, right? So the transformation is written like, so from x1 and x2, we transform into phi1, which is function of x1, x2, and phi2, which is function of x1, x2. In this particular case, the phi1 and phi2 are two Gaussian functions centered on the green crosses. And after that, in the kernel space, in this like carefully crafted two-dimensional kernel space, the data becomes linearly separable, which is nice. And in this class, we're going to talk about, say, kernel functions a bit, or basis functions in general, and there are a bunch of properties we'll learn about like how do you construct kernels. All right. Right, and the sigma is just a linear term for classification. So this is that probably should not have been here. Actually, no, sorry, the other way around. Right, so yeah, we're talking about classification. This page, yes, the sigma should have been there too. Right, so for regression, talking about this the other way around, but for regression, it's just W transpose phi. And the book has presented us with a menu of kernel functions, including polynomials, Gaussians, and sigmoids. So with Gaussian kernel functions, note that these are just Gaussians shifted and centered on different data points. Talk about, what this is and why this is in a little bit. And this is also still part of the recap. We have said that basis functions can represent almost any nonlinear decision boundary in the input space if we have enough of them, or if we're allowed to have infinite number of them, which is good news and bad news. And they can separate classes linearly in the feature space. So the important concept to recap here is the feature space versus the input space, right? The inputs are usually called x's, and in our textbook, the feature space are called phi's or something else. The basis functions seem to be able to do, for example, to do nonlinear separation for free for us. The things that it cannot do for free. And in here, for free sometimes means either more computation or higher dimensionality and so on. We should sort of mentally take all of that into account. But in terms of representation power, it does not remove class overlap. It cannot do that. And then the basis functions, we have to pre-specify it, right? So it cannot adapt its own shape to data. For example, the Gaussian basis function here, these, we have to assume that they are fixed width, or we have to pre-specify width, right? More generally speaking, we could mix up Gaussians from different widths, but we still need to specify which kind of width we need mix, which is important hyperparameter. But neural networks can be viewed as basis functions that adapts its own shape to data. That's why they are also preferable to an extent. what it cannot do is to adapt the number of features. But in this lecture and the next lecture, we're going to address that. So one can say that, for example, this one, right, it's just, okay, too bad. If my data from my class, input from my different classes sits on top of each other, there is nothing we could do, right? If input is all we observe. Maybe go back and examine how we generated the data. For the last two drawbacks, we've talked about neural nets. Now we're going to address the last one, which are good news. So So in this lecture, I'm going to do these things a few times. So there's quite a lot of talking, like what we have been doing so far. And then there will be a small chunk of mass in kernel density, and then a bigger chunk of mass in the kernel machines. We're going to basically forecast what we're going to say, and then come back to the goal and use the mass to go towards it. So here is like two of our overarching goals. So notice in this, let's say regression is approximated by W transpose phi of X. What we're doing is W, according to the normal equation, if you remember that, it's composed of the phi's, as we will see. The weights summarize the training data into a set of weights, right? Usually, let's say X in Rm or Rd, then W in this case, it's in the dimensionality of the kernel, it might be R of M. And the width of the length of W is fixed. So why don't we ask the features to adapt to the data? There are two advantages of doing this. One is, well, most targets sort of don't change abruptly. Like in the continuous feature space, there is usually a region that is, let's say, class A. There's another region that's class B. And then we would like to capture the general notion that essentially data points that are close together tend to carry the same label. That is the essence of pattern recognition, pattern classification, which I argue is like the gist of supervised machine learning anyway. Right, so you want to capture the pattern of possible targets in the neighborhood of the input. So the kernel formalizes these ideas. That's a reason to listen and to sort of anticipate what you're going to see. Well, another note is there's another suitcase word, or a word that means two slightly different things here. When we say a method is non-parametric, so this method up here, you can argue it's parametric in the statistical sense because we're expecting an m-dimensional parameter. So when we say a method is non-parametric, it means that it does not rely on a fixed number of parameters, which can be good news. So this can mean that it has no parameters, or very few parameters that are only hyperparameters, or potentially unbounded number of parameters, depending on how you look at it. And also, I put parameters in quotes because for some of these methods, the number of parameters could be as many as number of training points or order of training points, and that could, in theory, go to infinity, countable infinity, right? So this is sort of gives a bit more detail on what we mean by this loose definition of nonparametric, as we will see. So in today, how we cover the technical material going towards the two goals stated on the last page are three things. The first one is we look one simple statistical or data profiling tool that I'm sure most of you would have used at least once. It's called histograms. And then we look at density estimation, and then we talk about feature mapping and what kernels in kernel machines in machine learning kind of mean. We already said the word kernel is highly overloaded. In here, we'll talk about kernel density estimation, and the book also has these different other terminologies that are related. And this slide also lists this other particular sets of kernels that are connected to each other, which are already covered. So the general task that things like histograms tries to tackle, basically the goal of plotting, profiling your data using histogram is to estimate densities, right? So the assumption is I have n data points. They're drawn IIDs from some p of x. The goal is to estimate the p of x from data. You may say, this is similar, but not exactly the same as what we covered in the SML class so far. This is true because, the standard, supervised, and I'm going to overload SML, basically supervised ML. It works on basically X, Y, or X and target space, data tuples, right? And we have n of them, right? Let's say n equals 1 to be n, right? In here, we just have x's, xi, and we have, it goes from n to begin, and we want p of x. So density estimation is a classic task in statistics. It's actually also a very important task in machine learning. If you look at, for example, recent literature in the last roughly 10 years in ICML and so on, there are many papers that address density estimation directly or indirectly. So it's an important task. You can think of it as unsupervised, right? So things like Gaussian mixture models are certainly one density estimator. So there's that, right? So let's look at what density estimation in one dimension looks like. I have my input measurement x, and I have 50 data points. And the generating distribution is this green curve. You can see that it has two modes, right? Something like one smaller bump versus by one higher bump. Both are sort of roughly the same width. And when I have 50 data points, you have this all the time, right? So if I have, for example, for our quiz scores, we had 287 input entries. And then what Josh presented to the class was, hey, a histogram binned at 5 points per bin, and that tells us how many people are in each bin. So histograms are really widely used. But in this plot, we kind of examine, what's the effect of the width of the bin? If I bin too coarsely at the bottom, it does not show the two modes at all, right? What I see from there is, if I just read this, let's see, okay, there's no mode in the distribution. If I see from this, maybe I will try estimate the density as continuously growing towards the right. And if I use the top bin width, which is very fine, I might be seeing like, okay, Yeah, maybe there are 3 modes instead of 2, and the last mode may not have tapered off here. Right. So how many modes is ambiguous, right? So because the book crafted this very nice example, the middle one seemed to be the nicer trade-off, although because the histogram estimates are piecewise constant, we can't be sure where the mode exactly is when we only have 50 data points. So when we have an infinite number of data points, maybe the histogram will look more accurate. So what you do in a histogram, stated slightly more formally, because we'll need it, we'll build on this definition, is we partition the space into bins of fixed width, delta. We count the number of points in each bin. And then we normalize basically the probability, piecewise constant probability is the number of data points in each bin divided by the total number of data points, fraction of data points in each bin divided by bin width. So why should you use and should not use histograms? The advantages is if I try and construct a histogram, I can actually just count each data point once and then discard them afterwards. So if I have sequentially arriving data, I just need to look at each data point exactly once if I know where my bins are exactly. And if I have online data, let's say you work in an internet startup and you wanted to sort of estimate the densities of something this week versus last week, you can just sort of discard or gradually update your histogram by forgetting the older data, right, which is handy. So the cost for storing the histogram itself is fixed given bin width. It's the same point that we made about discarding data. And this is good for quickly visualizing densities in 1 or 2 dimensions. Okay, I'll pause a little bit and ask, what does a 2-dimensional histogram look like? So people can chime in and I'll talk about the cons and we'll come back to this. So the drawbacks is that, well, we have to know the bin width. In a lot of cases, when we just, let's say, oh, you're starting an honors project and your supervisor comes in and say, hey, here's some data and do your project on it. You don't even know the data, but you have to somehow know a bin width in order to start making sense of the data. That sometimes is undesirable. But if the data is already stored on disk, you can usually first try some bin widths to see, but profile the data with the percentiles, min and max, so that you can choose a bin width. And another thing that's not so desirable is that it has discontinuities because of this piecewise constant business. And it does not work well in 2 dimensions because of the curse of dimensionality. In more than 2 dimensions, we'll have basically exponential number of bins that scales with the number of dimensions. So that's bad. It also relies on an implicit assumption. So in these Euclidean spaces, we're just saying, it's relying on the sense of the distance within a local neighborhood. So points that are not far away, not more than X away from a bin boundary is counted in the same bin, right? In between 2 bin boundaries. Right. Let me reiterate. So what does a 2-dimensional histogram look like? I hope some of you would have used it just to check. Right. So Yu said it's the, like, it will become pillars in the two-dimensional space. Runza said heat map. Yes, great. Thank you both. Yes, indeed. So my personal favorite is the heat map on the appropriate color scale that reflects basically the one-dimensional higher and lower metric rather than the bipolar heat map. And the pillar view I generally do not like and do not advise my research students to produce, because a 3D map is subject to perspective distortions, and it can be hard for me to compare which column is higher than the other one. I know Excel does it for you, but not for quantitative comparisons. It's just eye candy. Great, thank you. So in order to address these drawbacks of the simplest density estimator we have, right, don't get me wrong, histogram is still sort of very widely used. And in fact, the heat map or 1D histogram should be our go-to tool for understanding the data before we do anything more sophisticated. Right? Related to histogram, you also have things like box plots, violin plots, and so on, and they are nice and give you a bit more information. And violin plot is actually very related to what we're going to talk about, kernel density estimators. So let's get to it. So in general, kernel density estimators are also called nonparametric density estimation. So in this particular case, the word nonparametric meaning very few or almost no parameters. So the scenario operating, again, is we have n data points, IID, from some px in d dimensions. And we can compute the probability mass in a small region R. If we know P of x, we can basically compute essentially the probability of the point x falling in some predefined region R by integrating over that region R. And if we randomly draw big K points, the probability that these K points falling within region R is binomial probability of these points, any point falling within region R, right? So we covered binomials, right? Basically, if we have n total points, the binomial probability is essentially n choose k times p raised to the power k, and then 1 minus p, basically I think this is a typo, right? So big M minus K points falling outside of region R. So we said the binomial when n is large, roughly looks like a Gaussian, like bell shape, right? For large n, what this means is the Gaussian is peaked around the mean n times p. Or it says the expected number of points falling within region R is n times p. And for large n, if we also assume that the region is sufficiently small, we can approximate basically the density in that region as a constant. Then we can also write the probability P as the density times the volume of region R. So there's a whole bunch of approximations here. Right, the point being made in the book it's actually not self-contradictory, right? So we want for the volume V of R to be sufficiently small so that the probability PDF function P of X is roughly constant. We also want the volume of R to be sufficiently large such that, right, so the binomial of probability K is peaked. If we're only expecting to have 1 point or less in the region, then yeah, the model is not going to be very good. We are, a lot of us are engineers and computer scientists, computer engineers, so we can understand the value of trade-offs, and we work with them all the time. And this is a trade-off, right? Basically, there is a sweet spot in between this, right? So we want V to be large and not too large, much small but not too small. And this slide basically is the sort of abstract view of what the two things we can actually do. And we'll walk through them in the next few slides or section. The first one is we fix K. It leads to an approach called K nearest neighbors. I'm just going to say in machine learning, there are two very popular things with the name K in it. So this is not the same as K-means. So K nearest neighbors is used for density estimation and classification, but not clustering. And then we can also fix V. It leads to kernel density estimates. And they have, despite being simple, these approaches have guarantees. Right? So K nearest neighbor density estimators and the kernel density estimator, both of them, right, converge to the true probability density in the limit of n goes to infinity, provided V shrinks suitably. We're not going to go through that technicality. And K grows with n. So this is a result from 1973, almost 50 years ago now. So let's talk about kernel density estimates first, and then K nearest neighbors. So the estimation recipe for a sufficiently large K and a sufficiently small V is as follows. We simply estimate P of X as K over N times V. This is, yeah. N and V are for normalization. And one example for doing this is to look at hypercubes. Basically, the kernel function K as being 1 with like this deviation from the origin to be no more than half and 0 otherwise. And the count of number of points within the little kernel window is basically sum over the data set to see how many points fall in this kernel window. Okay, how many points? Let's say plus minus a half within. This is in the sense of the previous equation within xn. Right. And the probability of x is simply the volume is actually this is plus and minus a half of h distance. So the volume is h raised to the power of d, and these are this component is k, and this bit is n. After we go through this motion, we realize that, well, hypercubes are essentially histograms, right? So what we have spelled out here is just a fancy way of doing histograms, because the windows are exactly squared or cubed in high dimensions. But we say that histograms are bad because it has discontinuities and boundaries. If 2 points are nearby, but they lie on either side of boundary, they're going to count for completely two completely different cells, right? And we know enough smooth functions that we can fix that. One of them is the Gaussian. So we know that the Gaussian window is a valid kernel. And what we do is, let's say the Gaussian kernel is written as follows, basically the x per term here. So the Gaussian kernel is proportional to the exponential of the negative square distance scaled by a bunch of scalars and normalized by the data set size. Note that I haven't written exactly the window, but this is the expression for the end estimate, the P of X. Right, and we can choose different widths, kernel width H. This is the example we saw earlier with histograms. We can see that we can, similarly as we vary the histogram beam width, we can also vary the Gaussian size. Let's go there. So we have, for histograms, we have the beam width at 0.04 all the way to 0.5. And here, for the size of the Gaussian, here, we have H equals 0.2, 0.07, and 0.005. We can see that in the top view, almost every data point, because there is a Gaussian that is centered around every single data point here. So there are 50 data points total. Let's say we number them from left to right. And so there's x1, there's x2, definitely is here, and x3. There might be x4 in the same thing because it's hard to tell whether there's probably 3 peaks and so on and so forth, right? So these are one data point, and these are multiple. As you can see that if the beam width is too small, we're almost looking at a smooth version of every single data point. And what it does is it's not estimating the density around these data points that are far away from others particularly smoothly. And if we choose H equals 0.07, this looks a bit better and approximates the true generating distribution in green a bit better. 0.2 has the same drawback of a histogram that's too wide. It generates a smooth estimate, but it does not give out the same, like the 2 modes that we knew that were there. So for kernel density estimates in general, we need to choose a kernel function that's non-negative, and we need to normalize it so that it integrates to 1. The good news is that, well, we simply store the training data and we don't need the computation. What does that mean? It means, right, so this equation 2.249 is the general recipe for computing kernel density estimates by plugging in this k function. So we don't need training, but to evaluate the density at any given point, we basically need to go through all the data points. So we don't think of the act of storing all data points for training, but at testing time, at evaluation time, we just need to go through all the stored data points, and this is rather expensive to evaluate. So compared to the y equals w transpose phi of x, where w is fixed dimension dimensions, and it doesn't grow with respect to the training data size. But in this particular case, the evaluation grows with the size of training data. So this is a view that's useful to have, let's say, and we actually can use this view to connect the kernel methods to the kernel density estimates. They're not, again, completely separate. As we saw a few times, a lot of things are not completely separate, right? So let's, we said we're going to talk about this thing called k-nearest neighbors. Right, if we were going to criticize kernel density estimates, it's because they fix the volume V. There's no adaptation to the data. We have to choose the kernel beforehand. And we have to choose the width. We can come up with an alternative. As we said, right, the volume, kernel volume V is quite a critical parameter. It cannot be too big, it cannot be too small. How about we try and ask the data to like find its own V, right? One way to do this is to consider a small sphere around each data point and then allow the radius to increase until it contains exactly k number of data points. And we set V to the volume of the resulting high-dimensional sphere. So this is the result when we ran it on the two-mode synthetic data set. Right, so for k, we can choose basically, now the hyperparameter is k, how many neighbors do we want? And if k equals 1, k over n, for k fixed, k over n is a constant. And then this constant times 1 over V is the density estimate, right? As we can imagine, if we're sitting on one of the training or observed data points, this volume shrinks to 0. V goes to roughly 0 when x, loosely speaking, when x approaches xn, any of the training data points. So that explains these unbounded peaks right in here, where v 0p of x approaches infinity. That's why the slide says it's not producing valid density estimates. What about, right, what about larger k? I can require, for example, estimate to have, let's say, 3 or 5 or even more points in it. It suffers, well, again, there is a middle ground for choosing k. Number of neighbors for different data sets. But again, you're not necessarily guaranteed to find it, right? So if k is too large, it can become, the estimate can become too coarse. But in practice of machine learning, this is another hyperparameter we can sweep through. We just looked at k-nearest neighbors for density estimates. Now, despite it doesn't produce proper density estimates, we can actually use it for classification, which we don't need P of X. What we need is probability of the class label given X. And this particular scheme is called k-nearest neighbor for classification. So what we do is, if we want to classify a particular data point, we draw a sphere centered on X, containing precisely k different points, irrespective of their class. And then we make them vote, like simple majority vote, to be like simple, which can choose k equal to some odd number. The nice thing is, again, in the roughly 50-year-old result, in the limit of infinite number of points, the error rate of one nearest neighbor is never more than twice the minimum achievable error rate of an optimal classifier. Like i.e. if we know what the true class distribution is. So that's very nice. This result is due to Thomas Cover and Peter Hart. So this is in the k-nearest neighbor classifier, a new point. If we want to classify this point, we can look at, for example, its nearest point, or we can look at a few more like nearest points. And in general, k-nearest neighbor classification incurs piecewise linear boundaries like this. I'm suspecting this particular diagram is missing points, but I'm not completely sure. I can double check in the book and get back to you. Okay, Qinyu has the question of why not optimize K and V together? So, interesting question. It is a lot easier to think about controlling the behavior of something when we only have one control knobs rather than two control knobs that relate to each other. How do I say this particular thing? So in this case, if we're doing classification K and V on this slide, we fix K, we are implicitly choosing a set of varying V. If you want to, for example, fix K and then control V, you may not, you are no longer guaranteed to have the K number of neighbors anymore. And if you, for example, if you fix an upper bound of K and fix an upper bound of V and still want correct classification, you will need to think about a clever way of ensuring that that happens. And for density estimates, we have already said that doing k-nearest neighbors, meaning fixing K but don't constrain V, do not produce correct density estimates. So that's sort of a moot point. So you may ask, can you more or less fix V but also control K? Yes, there are many different smoothing schemes for if you don't have enough data points in a particular kernel. But it's, yeah, so there is no short answer to this particular one. In general, controlling two like degrees of freedom is a lot conceptually quite a bit harder than only having to control one. I hope that helps. So here are some pictures of, yeah, there's this oil data set in our book. It's actually real data. There are three kinds of flow dynamics. So this also is an interesting cultural example on how machine learning can be used in scientific engineering data, right? So if we have essentially water or oil flowing through a tube, we can classify. So if you are fluid dynamic engineers, they can be classified as laminar, annular, and homogeneous classes. Actually, there are also turbulent classes because machine learning for fluid dynamics is another emerging topic that lots of people are working on these days. And the different types of flow actually mean a lot of things about different properties in physics. So that's important, and turns out you could classify the different type of flows based on like measurements of the oil data. In here, they're using two features, X6 and X7. And as we can see, that larger K does not necessarily mean better classification. So this is quite tricky. We're also remembering all the training data points. And again, K equals 3 seems to be a sweet trade-off spot, but it's still not perfect because in these two-dimensional feature spaces, as we can see, some of these points really are sort of on top of each other, and that makes it very hard to classify, right? But if we only have 200 data points and we choose k equal to 31, we're making the 31 neighbors vote equally, then that's not very good. One easy fix you could try and imagine is you can do class conditional density estimation for each of the classes, and then you could compute the class posterior based on the density estimate. So that's sort of an improvement of the 2 or 3 ideas we just said. All right. So we talked about half of the stuff that we talked about. Now we're going to basically do another take on linear classification and tell you how to represent it in a different way. Before that, if people have questions, hit me. And this is switching gears to chapter 6. Given how much time we spent in the density estimates, I imagine this will take a bit more than half an hour. So just be prepared for that. So there is a little bit of linear algebra, not too much. And I'm going to signpost it. And I would forecast that just to say that you guys are responsible for this material in the quiz and final exam. So let's begin. Just a clarification on the terminologies we said again. So we mentioned parametric methods such as W transpose X, W transpose 5X. We mentioned non-parametric methods. Basically, so far I use training data, and we only choose K or the kernel or the volume of the kernel, and we also K nearest neighbors can also be roughly classified in this. So I do not feel parametric and non-parametric methods are terms being used a lot in the modern or in the machine learning research literature these days. When you see them, just be careful about what they mean. I would also just give a warning about, so basically between 2003 or 2005-ish until let's say 2015 maybe. So non-parametric methods can literally means, or there's a class of method called non-parametric Bayesian models. They refer to the latter class, basically a clustering mechanism that grows the number of clusters dynamically as they see data. And there are models with interesting names such as the Indian buffet process or the Chinese restaurant process. Ask me if you want to know what they are. It's kind of cool, and we won't cover them, nor will I advance the ML, but they exist. They mean the number of parameters potentially approaching infinity. Yeah, kernels. So the common spiritual things, or basically general ideas that are common between the kernel density or k-nearest neighbors is, there are something called kernel function that are in spirit similar to those, and then they're evaluated the training data, and we're kind of remembering the training data in some way. And some more terminology before we dive in is a feature is a measurable property of a phenomenon. Again, there's different names being used. Raw feature, often called input in this book. I think the distinguishing them by calling them input versus feature is good. But if you move away from the book, beware of what people mean when they say feature. A lot of times they mean input as well. And derived features, feature. Right. In this class, we're not going to touch on feature selection techniques. So features or input can actually be redundant. And some of them, so there are two intuitions on why we should select features so they can be redundant with respect to each other. Say two inputs are measuring roughly the same thing or highly correlated. And they can also, so we can also ask, are they informative of the target? There are many different approaches. We're not gonna, we don't have a chunk of content, but you could imagine like the information measures that we covered. For example, if the mutual information of one feature dimension and the target is 0, that means, well, the input and the target are kind of independent. Should we still take, do we still take into account of that feature? On the other hand, in the age of deeper and wider learning machines, the importance of feature selection have become less prominent because, hey, if we have a million learned features, why bother selecting them? Just use all of them. That's also to say that logistic regression is actually very robust to redundant and irrelevant features in practice, which is good, right? So the meta point on this slide is also to say that we are one of the holy grails in classic machine learning is to be able to do automatic feature extraction from an input. And to an extent, deep learning has kind of delivered on this promise, which is very nice. Kernel machines, to an extent, also delivers on this promise. So here is the mathematical goal we're going to go towards in the next little while. And this thing is called the kernel methods, right? So consider a label training set again, xiti. Now we have a learning target as well. And the assumption is they are drawn from some joint distribution of P of X and T. Except we're not doing density estimates, so we don't care about the P of X and T. And the prediction at a new point is basically a linear combination of kernel values, right? So in here, so the alphas are the weights, and the case is a kernel function here. So note that this kernel function is centered. Let me just quote unquote call it centered. Like if I can direct your attention or memory towards that Gaussian function where it has a fixed width and it's centered on some data point xi, centered on one training point xi. And then we basically sum over this overall training point. We get our prediction y, which can be regression or classification. Right, so what has happened? Right, so this is a major departure from y equals w transpose phi x. So instead of phi, we have k's. And for the case, there is essentially remembering all training points. And the kernel function, intuition of the kernel function is that it measures the similarity between two examples. You could also kind of hand-wavily read, loosely, right? Y kind of roughly is alpha I times some similarity of x, xi, summed over I, y of xi. No, actually y of x on a new data point. So the prediction is a weighted average of the training targets. And the weight depends on the similarity of x. We haven't gone down on this slide on what the weights should be. What are these things? You may say, oh, what are these things? Roughly, they depend on the similarity again. But let's get to that. And another reminder is why are we talking about kernel density estimates? Because let me just say that this expression, it looks like KDE expression P of x equals something like 1 over n sum over like divided by volume, the k of x and xi and so on. Okay, let's dive in. This is what we're shooting towards. Now let's come back to what we already know. So if we're doing, let's say, regression with least squares loss, this is what we've seen so far in chapter 3. And moreover, we're doing auto-regularized. Like, this is basically the mean square error plus L2 regularization that we see a lot. And moreover, we have this phi matrix. Basically, we write the different stack, the different phi's vertically on top of each other, and we get this phi m by m matrix, in which each row is a feature vector. Right. Remember that what we want to go towards is this thing on the upper right-hand side. So this is the goal for next 2 slides. And a spoiler is that this matrix, so-called kernel gram matrix K, is an n by n matrix, as we said, right? So K is sort of encoding similarity between xi and xj. So because it's going over data points, it's got to be n by n. Right? And moreover, well, from linear algebra, we can see that phi by transpose is n by n. Let me write that slightly more precisely. In n by n, and phi transpose phi is an m by m matrix, where m is the dimension of the basis functions. This is, we know this from chapter 3, meaning the normal equation for solving the optimal weights is as follows. If we examine this thing, we can see there is terms like there's phi t here, there's phi transpose phi here, and w is m length m vector. So this is not quite what we need. Because our goal is to come up with an n by n matrix, or come up with expressions involving n by n matrix. Nonetheless, we also remind ourselves that, well, this is a linear regression model, that the prediction on the new data point is computed as phi transpose w. Oh, phi transpose w and w transpose phi are the same thing, so it doesn't really matter which one we write first. We can just do that. It's convenient, which is written like this. Nothing new, right? So this is recap. Now, in order to come up with an expression involving K, the gram or similarity matrix, let's do some linear algebra. So in this section of the book, it's called a dual representation. I would just ask you to take it at face value. I wouldn't ask you too deeply about what dual really means. There's a section in chapter 7 that we could cover about the dual problem in optimization, but I would actually say leave that to advanced ML about what exactly dual means. So this is the objective least square loss, regularized square loss that we talked about. And we write it in matrix form, simply as this. And now the next step, what we do is to take the partial derivative of the j with respect to w and set it to 0. That gives us this expression down here. The next expression. Yeah, it just by now, because we're just verifying that it's correct, we can just squint at it and say, oh, the quadratic term involves phi transpose phi and lambda I, and there's a linear term here, and the rest, the linear term of w is like this, right? Phi transpose t. We arrange terms. So this is a slightly unusual step in order to allow for a construction to express the kernel combination weights. So just bear with it. What it does is that we preserve W on one side, and then like phi transpose phi W, we move that to the other side. We do this in order to define this alpha n, parameters alpha n, basically the weights for each training data as W transpose phi minus target. Basically, this is the prediction error on each data point. Xn, this part, and scale by this Lagrange multiplier lambda. You may ask, what have we just done? We just did a bunch of manipulation. It's purely linear algebra. Now what are we going to do? We now have defined this new alpha symbol, which is a whole bunch of things. That seems somewhat meaningful. And we just said, now instead of writing W, I'm going to write phi transpose alpha as a matrix times a vector. Right, and then I'm going to just plug it in back because I now replace W with alpha. Indeed, right, alpha has W in it. I have not reduced my essentially unknowns. In fact, right, so alpha as a vector is n dimensions, but W as a vector is m dimensions. Now I just change one from this m-dimensional vector to n-dimensional, and then I just plug it back to j of W, and now call it j of alpha, because alpha is the variable now. You can easily verify that this is the case by expanding the quadratic term. For example, the last term, like lambda over 2 W transpose W is simply this, right? W transpose is alpha transpose phi, right? So transpose flip the order of products and phi transpose alpha. All right, so that's nice. So where are we going, right? You can verify the front part, right? Let's not do that in the real time. So what we're going is we want expressions that involve phi transpose, not the other way around, right? So not phi transpose phi. As we said in the last slide, phi transpose phi is the round dimensionality we want phi transpose. I know it's a mouthful, right? Now we can verify whether this sort of fits our bill. Let's do that, right? So this is phi transpose. Great. There's another term here. Oh, there's two of them here. Right, we're getting to something, it looks. And this is a square matrix, so K transpose is also K transpose is K. So that's nice. Okay, let's do that. Take this long expression, which is here again. And now we define the n by n kernel matrix called K, phi transpose. In particular, the elements of K are computed as like, because this is phi transpose, we can essentially do the multiply and because each row in phi is a feature vector, so each element in K is the inner product between two feature vectors. And we simply call it little k xn comma xm. Just bear in mind it's the inner product of features. And for a new data point, like, okay, or let's say x not in x I goes from 1 to n, then we can compute its kernel value by still taking the inner product of the feature vector of the new point, and then this is the feature of an existing point or training point. Let's call it training point to avoid confusion. And this is handy when we try and make predictions. All right, so now what do? We just take this expression 6.5 that we got on the last page and rewrite it with k's. Okay, that looks a lot better, right? Because if having this phi transpose everywhere is really an eyesore, right? It's a long expression. So we can now see this is quadratic in K, and these two, they're linear in K. And this is constant, right? But that's not the way we can see it. What we want to solve for, so this is an expression that's quadratic in K. It's also quadratic in alpha. Right? So here, this one and this one, they're quadratic in alpha. And this one is linear in alpha. And the t term is still constant. Great. And it's a loss function with respect to alpha, the weights on each training example. Now we can solve it, right? We already know how to solve these kind of things. Yeah, after some more linear algebra that we won't go through, we get alpha equals k plus lambda I of n dimensions, take the inverse times t. So I think it's not too difficult to convince ourselves that, because this looks like a regularized L2 loss for alpha as well, this should be reasonable, right? And remember that W, the alpha and W essentially have one-on-one mapping. So we can recover W from this as well. So how do we make predictions? We just go from the old expression, W transpose phi, sub in alpha for W, and sub in this essentially the equivalent of normal equation for alpha. In this expression, we get k of x transpose times this inverse of the regularized kernel function times t. Okay, so what has happened is, so in here we're doing inverse of an like n by n matrix, and in the kernel function, so where are we, you might ask, where are we remembering all the training data? So they're remembered in two places. So this is pairwise similarities of training data. All the set of x n's, called little n's now, right? And furthermore, in here, So this is similarity of the new x with all of the xn's. This one is specified here. Right, so basically, the k of x as a vector is computed as a vector each of which contains a similarity value between the new point with respect to every single training data point. Right. So how does this compare to linear regression that we had before? Is to compare with the linear regression function. So if we use normal equation to get W star, we're essentially also, right, all the training points are summarized here, right? Phi transpose phi, yeah, in this, yeah, this regularized term, right, T, right? And this ends up being the W, the m-dimensional vector. In our case, the T is still there. So if we talk about pre-computation, right, during training, so this is pre-compute. During training. And this yields a vector that's n-dimensional. And these will become weights of the kernel function value for the testing point. What am I saying here? So there was a thing that we're going towards, which is here. Right? So let's see if I can. Right here. Okay, so I cut this point out. Oh, copy it. That's silly. Right, so basically for this particular part, we're going towards alpha I times the kernel value of the training point with all the, like the new data point. Okay, can I just copy it? No, oh, right, okay, great. Then I can post it here. It's a bit smaller. Right, so for this goal that we had a few slides ago, right, this K part is basically this part, and then the alpha part is this part. Now we delivered on Go. That's pretty much it, actually, except we haven't talked about how to construct the kernel functions. I'm just going to pause because this is like the most, like the majority of linear algebra we're going to be doing. The constructing kernel one is sort of easy compared to this one. If there's any questions, hit me. If not, I'm happy to digest this a little bit. Right, so maybe let me just preempt the last little bit, which I think need about 10 minutes, by saying, so what, use a different color. So what is this kernel function k, x, and xi? In the next little bit, we're going to talk about two ways of thinking about it. The first way is to explicitly work it out using phi of x. Right. So this one I would say it's not a lot of surprise and new content because we started this lecture saying that we were not quite happy with phi of x and we wanted to improve upon it. Now we say, well, obviously we can define the kernel based on phi of x. So on the last page, look, the kernel is defined of phi of x. The second way is to say now phi of x it exists, but it could be implicit. We can still have so then we make basically the k of x I x j is the first class citizen. That is, I think, the sort of the selling point of kernel machines is that we don't have to have an explicit phi of x, which can be sometimes messy and hard to get. The extreme version is the phi of x can be infinite dimensional as well. But k of x can be simple to compute. I'm not going to go exactly there, but let's show you roughly how this is done. All right. So that's corresponding to chapter 6.2. I'm also going to admit that we're not going to be very precise about what makes a valid and good kernel function. For now, I think we should think about, like, let's say, loosely speaking. So k of, change color. Kernel function of x prime, it should encode some similarity. Meaning being bigger when the 2 points are closer together in some space. It should be symmetric. Or most of it should be symmetric. And for any data set, of any countable size, like any size, the K matrix is roughly positive semi-definite. So for the purpose of this class, we assume these three things. Doing this more formally involves what's called the reproducing kernel Hilbert space. We are not going to get into that. Like one of the previous slides have this exact word. Let's not get into that. So, okay. When we talk about kernel function, we mean the inner product of the two, like the feature function of the two respective data points. Right. And the kernel function is defined of two data points of the input space. So because we were sort of moving towards, we wanted to get rid of explicitly having to write phi's. Therefore, we write kernel k of x prime. Right. So it's symmetric. We assume it's symmetric. It's the inner product of two basis functions. As we said, at prediction time, we evaluate the kernel function at the training data points or a subset of training data points for Wednesday. That's where SVMs come in. Here are some example kernel functions, right? Given that we said we can do the inner product of phi's, let's just look at if we say, what about we just do the inner product of two vectors and square them? And furthermore, we assume, let's say these two vectors are both two-dimensional, x1, x2. And z1, z2. Right, okay, inner product is x1, z1 plus x2, z2, and then we just expand the square, and that gives us this thing, right? So x1, z1 squared, both squared, and then the cross term 2 times x1, z1, x2, z2, fair enough, and the second term both squared. The question is, yeah, it's weird, right? So in here, this is inner product inside. But the requirement for the kernel function is that the whole thing being interpreted as the inner product. Therefore, we need to rewrite the squared inner product into a form in which there are two vectors, the inner product are being computed. The first one need to only involve the x1 and x2. And the second one needs to only involve z1 and z2. Okay, that's doable because your algebra skills is great, right? We basically look at each of these terms, just separate out the x terms versus the z terms, and we're done, right? Well, because x and z are different, just different notations. In here, phi of x is simply x1 squared, x2 squared, and x1, x2, scaled by square root of 2. So that is quite a nice separation, right? So basically, this is, let's say, like this features of polynomial order of 2. So this is quite nice, and it can simply be computed without explicitly writing out the features. We can just compute the inner product of the original vector and square them. You may ask, right, so the most obvious features of polynomial order of 2 can be x1 squared, x1, x2, and x2 squared, right? So you can say I have phi prime of x equals this. Will that work? The short answer is yes. Squared. You can also say, oh, I can find x that not just have the quadratic terms, but also have the linear terms, right? x1, x2, and x1, x2, and x1 squared, and x2 squared. And why don't I throw in the constant as well? So that's also going to work. But in that case, as we will cover in feature composition, like, yes, it's also going to be a valid kernel as well. Right, so this particular blurb in the book covers what we said informally. Right, so a necessary and sufficient condition for a function to be a valid kernel is that the Gram matrix, this kernel matrix should be positive semi-definite for all possible choices of the set. Right, so note that a positive semi-definite matrix is not the same thing as the matrix for which the elements are positive, are non-negative. So this means all eigenvalues are greater or equal to 0. All right, let's move on. So, right, kernels, basis functions, and similarity computation, they're all connected now in our head, or hopefully after you absorbed the material here. So these are the same pictures from chapter 3 as in basis functions, except we're now looking at the whole, like the bottom row, where, for example, for these Gaussian basis functions, if we denote this point as x prime, then the kernel value, right, this is basically a kernel of x prime for one-dimensional Gaussian. right, the corresponding kernel function look like these. You can see most of them have different wiggles and they have sort of a width of the primary mode, so to speak. It might sound a bit surprising that the drastically differently shaped basis functions all result in kernel functions that look somewhat like each other. That is because basically the structure of the inner product of phi x transpose. But for now, for example, these pictures are good intuition to have about what the kernel function is actually doing. They're also a good intuition to understand the connection between the weighted sums of kernels with respect to the kernel density estimates we talked about earlier, right? If we're doing a weighted sum of these kernels, the kernel density estimates are actually an unweighted sum of kernels, right, if you will. And the weighted sum of kernels is sort of connected to kernel density that way. All right. I think this is the second last technical slides. The book has this recipe on constructing new kernels. You may say that so far we know that, what do we know? We know X transpose Z, okay, kernel of X prime, maybe X prime. Like, no, okay, X transpose X prime is a valid kernel. X transpose X prime squared is a valid kernel. And we know not much more than that. So what are the ways of coming up with other kernels? Are these the only kernels? Obviously not. So here are some of the algebraic operations that can essentially give us kernels based on new kernels, existing kernels. So that's okay. That seems to be useful. So if we multiply a kernel with a constant, it gets us a new valid kernel. We multiply a kernel with like two functions on each side, or like one involving x, one involving x prime. That's a valid kernel. If we pass the kernel functions through a nice function, such as exponential function, it gives us a new kernel. The sum of new valid kernels are valid kernels. The product of two new valid kernels are kernels. If we chain the kernel function with a valid basis function, then it gives us kernels. And if we put a like symmetric positive semi-definite matrix, it gives us a kernel. So that's if we partition the input vector into two parts and compute the kernel on each of the parts and add them up, they give us kernels. And so that's the end. If we multiply them, they still give us kernels. So for example, this one takes care of the linear and quadratic term that we talked about for the order 2 polynomial kernel, right? So these recipes seem to be useful. I'm not saying they're exhaustive, but they're useful. And you might get an exam question or so about this because they're easy to make exam questions. Anyway, so that's informally. Formally, constructing kernels is a useful skill, and also examining things. For example, we can have a kernel function that looks like a Gaussian, scaled Gaussian, like without a bunch of constants in front. You may ask whether this is a useful, like valid kernel. Turns out it is. So what we do is we invoke the property. This is of f of x, and this is exp of essentially kernel of x prime scaled by a constant, and then f of x prime. So we basically use, so from a linear kernel, and this kernel is simply x transpose x prime. So from a linear kernel, we first scale the whole kernel, we then exponentiate it, and then we multiply two functions of each variable to it, we get a valid kernel, which is a Gaussian RBF kernel. You may ask, right, so in here, phi of x is x right? You may ask, what is phi of x? The answer is that's non-obvious. What this whole page of kernel properties allow us to do is to basically think about kernels as compositions of other kernels and gets us away from thinking about phi of x. So as I kind of hinted, the phi of x for Gaussian kernels is infinite dimensional. So yeah, let's not go down there. Okay, further example kernels, right? As we kind of hinted, the inner product of vector inner product raised to the degree m. It's a valid polynomial kernel of only terms of degree m. If we want all terms up to degree m, one useful trick is to just add a constant to it and then raise the whole thing to order m, and that's an easier way to compute, right? So as you can already see, so this is easier to compute than and lower dimensional than having to compute phi of x. Transpose phi of x prime. The Gaussian kernel we talked about, sigmoid kernel is not a valid kernel, but people use it anyway. It's a whole bunch of unusual things happening with the sigmoid function. Right. In general, we have names for the commonly used kernels. For example, when people say polynomial kernel, you need to clarify which one of the above it is. But x transpose x prime is called a linear kernel. And if a kernel is only depend on the distance, assuming L2 in here or some other distance that needs to be specified between two data points, then it's called stationary kernel. Moreover, if it's only depend on the norm, or so this is only depend on the difference, depend on vector difference. All right, vector difference. Depend distance between the thing. It's called homogeneous kernel. So the way to imagine homogeneous versus non-homogeneous is basically a ball versus a rugby ball, like between x and x prime. Imagine one of them in the center and whether the distance is sort of the same along all directions or not. So there's a culture node on we can define kernels not just in a vector space, but also in some structured space, such as graphs, strings, and sets. This is actually quite connected to all the recent literature about graph neural nets and so on. So there is a whole body of literature called graph kernels that computes distances between graphs and, let's say, strings. Some of the neural net operations can be interpreted, or graph neural net operations can be interpreted as approximating that. So that's a way of understanding things. The book gives an example of basically the intersection of sets, the Jaccard distance of sets, or basically intersection, but not without a normalization, raised to a power they correspond to an inner product in some feature space. So the truth, yes. So I am not sure if the intersection of sets is a kernel function, but the expert version of it definitely is. We can also define a kernel through a generative model. The general idea is to think of kernel as p of x times p of x prime. Yes, that's a similarity function because when both of them are small, they're not necessarily similar, but both of them are big, that they're similar. So that seems to be reasonable. Even if they are reside in different modes, we can also think that it's sort of a similarity function warped by the multi-mode probabilistic PDF function. And we can include a weighing function, extend the kernel in this way that's similar to introducing a latent variable. We're not going to cover hidden Markov models this semester, but you could think about graphical models like those induce an implicit kernel function as well. To summarize what we said, we have encultured ourselves on picking a suitable kernel function for density estimation and also classification and regression tasks. So for linear regression, we go from this, basically this summarized into a W vector to the kernel vector of the training point, and this set of weights alpha summarized into this n-dimensional weight vector. Right, so the talk we just had about implicit kernel functions or composing kernel functions is now the nonlinear transformation is implicit rather than explicit via phi of x. No need to write out phi of x. So that's pretty much it. I don't know if people have questions, whether all of that have made sufficient sense or not. We've covered mainly two fairly distinct ideas on density estimates, nonparametric sort of estimates and kernels. Turns out they are somewhat similar as well via, for example, this particular expression, y of x. People don't seem to have questions yet. So I'm going to stop sharing and wait for maybe 2-3 minutes and see if people come up with questions. Oh yeah, okay. Qingyu again. Thanks for contributing. The others feel free to ask as well. Is kernel more flexible than the basis function? If the original linear model with basis functions can do the same thing, why use kernels? Good question. Right. Thanks for that question. I think these are different set of tools. In some cases, it might be easier for us to think about explicitly transforming the features. For example, if we have, let's say, a bunch of user interaction features, or if we're doing recommender systems, there's, say, a whole bunch of movie features and a bunch of user features. They are not too high dimensional, and we hypothesis there is nonlinear interactions among them. Then maybe we just throw in the polynomial file, second order, third order, and see what happens. If that improves the result, then maybe our job as an ML engineer is done. In the other case, like we were not sure, for example, whether it's polynomial interaction are gonna help. So in today's lecture, we are looking at kernels as a new tool of not forcing us to think explicitly about the phi of x or polynomial features and so on and so forth, but we can express basically the similarity of data points in different ways. That sort of, I thought, give us a whole new space to play with how we engineer our machine learning models if we are going to use it. What does that mean, right? So another spoiler is, so there are several benefits of using kernels. I mean, it's informally, right? This benefits of using, let's say, the kernel representation. It can, right? So phi of x can be implicitly high dimensional, like even infinite dimensions. We can, I think, being able to compose new k from existing k, that seems nice. Like we can just square a kernel function and exponentiate them, and they can, right, that induces a drastic effect on the phi. We can also say, oh, we want a linear and non together, then we can, yeah, for example, we can compose the Gaussian kernel function or the first and second order polynomial function, and they all work. And as we see on Wednesday, so we can have spas, like alphas, that correspond to SVM. And sparse is equal. Sometimes, depend on your training data, sometimes it is sparse, sometimes it's not. But it's, again, a new tool set. What else? Right, so RBF SVMs, it can be viewed as essentially weighted nearest neighbors too. I think I spelled that wrong. B-O-U. And it could be like sparse or not sparse weighted nearest neighbor, all done through a convex optimization framework, which could be nice. All in all, it's a new tool set, right? So we are engineers, or I approach machine learning as a sort of an engineering subject where we have this toolbox. If you're going and fix something in the house, you have a toolbox. Not every tool needs to be used at the same time for every task, but having a new tool that sits there is not a bad thing. Okay, what are the bad things about kernels? Right, one of the things, okay, bad. Okay, cons of kernels is that, look, okay, it's n by n. Just computing it is order of n squared. If you're working for an internet company and you have millions of data points, computing out the whole kernel is not going to be too easy. If you have tens of millions or even billions of data points, then you can probably forget it, or unless you do some clever linear algebra approximation. So, moreover, okay, inverting kernels. This is basically inverting the kernels. Regularize it, basically add lambda to its diagonal, and then inverting this thing is a killer. Order of n cubed. Oh, that's bad. That's also why we don't just brute force solve this thing for SVMs. And that's why we need to spend the next lecture talking about SVMs. So that's a long-winded answer to your question on whether kernel is more flexible. I hope that helps. I hope I've ranted for long enough. I'll see you on Wednesday. Stop the recording and disappear in a few minutes unless you stop me.